Hi everyone, I'm Zahra Safidgar from a Smart Thermal Energy Systems group at DTU Technical University of Denmark. In this tutorial, I'm going to show you how you can model your chemical reactions by using COMSOL multiphysics. First, we are going to talk about fundamental of chemical reactions, and then we want to know how we can model these chemical reactions and turn it to the mathematical equations. Then we can use these equations on our simulation, and then in the last step we're going to do a simple example at COMSOL. First, there are different types of signs and equations for chemical reactions, but the basic is same as this one. A and B represent a species of reactant, and reaction goes forward. This sign shows a one-way reaction, and C and D product can be produced. If anywhere you saw this sign, it means this reaction is reversible. It means it can go forward and backward. And also this is a sign of equilibrium reaction. Reactions can be exothermic, generate heat, or endothermic, absorb heat from environment if the physical state of all species is the same. This reaction is homogeneous. But if at least one of the species will be in another physical state, like for example like here, this reaction is heterogeneous. Reactions can be for different purposes, like synthesis, similar to synthesis of sodium chloride, or for decomposition, like decomposition of calcium carbonate, and also single or double displacement of any element of a species in a reaction. Usually we want to our reaction go to the desired direction, but sometimes there will be some side reactions or undesired reactions. The main reason for this phenomena is that the environment of the reaction, means inside the reactor or reactor chamber or something like this, has some higher amount of species that we do not want to be in the reactor. Unimolecular, when there is only one reactant, this reaction is described by the first order. And biomolecular means there are two reactants, and the terminology that we use for describing this kind of reactions is second order. But thermomolecularity or third order reactions are very rare, because if there will be three different kind of species inside the reactor chamber, the correct direction and energy and speed, these three molecules should collide together to initiate the reaction and produce product, is low chance, has a very low chance. Therefore, these kind of three molecular reactions are very rare in nature. Usually we're using elementary equation to describe our chemical reactions, but in most cases the mechanism of reaction is not as much as simple. There are several reactions. As I said, this is a simple form of writing a chemical reaction, and this small a and b, the purple color, are a stoichiometric coefficient. There are some questions. If we have this chemical equation, chemical reaction, is this reaction possible? Is this happening? And if it's happened, what conditions are required to make it possible? And then what is the final energy state? These questions are related to the realm of thermodynamics. When we're using first and second law of thermodynamics to find temperature, pressure, enthalpy, entropy, and Gibbs free energy. Also, there are other questions like After this reaction happened, how much of the reactant was consumed and how much of product was produced? What is the final concentrations of reactant and products in the reactor chamber? It means, what is the extent of a reaction? These questions belong to the realm of chemical equilibrium. When we use law of mass action, we're going to find equilibrium constant. Chemical equilibrium, if you want to show it with more diagram, it's something like this. That assume that blue and red dots are A and B species, and this is a reactor at the initial time. Therefore, these are the initial concentrations of reactant. After equilibrium, there will be all four species inside the reactor. It means that the concentrations of all reactants and products are at the equilibrium. You can see these diagrams, which shows that the concentration or amount of reactants will be reduced and the concentration of product will be increased. And at the specific time, which this time shows the equilibrium, the amount of reactant and product by increasing the time will not change. This is the diagram, but it based on the different reactions. The concentration of reactant and product will be different. Like in case 1, concentration of product and reactant are the same at the equilibrium condition. At case 2, concentration of product are much less than reactant, and the case 3, concentration of product is much higher. And this case 3 is something that we are seeking in our simulations and in the reality. Also, there are other questions that if this reaction happened, is it fast or slow, or how much is it fast? Like it's like a firework, very super fast, or it's like a iron rusting? What is the rate of reaction, and what factors affect the rate of reaction? All these questions belong to the chemical kinetics. Let's wrap it up. All 3 topics that we discussed: thermodynamic, when we are going to find out more about the thermodynamic conditions, pressure, temperature, enthalpy, entropy, and Gibbs energy, and we're using first and second law of thermodynamic. And the equilibrium, the question that we want to answer is the final state of a species. We use Van 't Hoff and Clausius-Clapeyron equation. And in the kinetics, we want to know how fast is our reaction. We want to know about the time, about the rate of conversion. And for that purpose, we use Arrhenius equation. By this introduction, let's go to the modeling of chemical reaction. Usually, this equation is used to describe a reaction. The name is reaction rate, and X here had different names in different literatures, references, and books. Extent of reaction, degree of conversion, reaction conversion. So this equation consists of 3 different functions. First one is a function of temperature. The name is the rate constant. For this function, we use Arrhenius equation. And for using Arrhenius equation, we need 2 parameters, A sub 0 and activation energy. How we can find these 2 values? By using the result of experiment. And if you do not have any experiment or do not have access to any data or result of experiment, you can use literature, you can use different scientific papers. Second term is the reaction model. From this table, you need to choose the correct model, but how we can find which one is proper for our simulation, it also depends on the result of experimental tests, or you can find it in the literature. Last parameter is the pressure dependent term. Again, you need to find out which one of these force mechanism you want to choose. But mostly I saw linear and inverse term, but also it depends on your case. The temperature and pressure of equilibrium can be related together by using this equation, Clausius-Clapeyron, and only two parameters, enthalpy and entropy of reaction, needed to solve this equation. Now I want to introduce you COMSOL Multiphysics, which is very famous software. This software is one software environment for any engineering field. It means we can use model builder workspace to combine different physics to describe our phenomena. Everything can be done in model builder, from building the geometry to the end, seeing the result and optimization. And next workspace is application builder. When after simulating the model, usually engineers want to make a simplest and more user-friendly simulation app to can be used by customers or collaborators, which these persons are not expert to use COMSOL. And also the last workspace is model manager. When by using this workspace, managing, controlling, and organizing models and simulation app can be easily done. But if we want to simulate a reaction, we need to use reaction engineering model. There are two steps. First is that simulate only and only the reaction mechanism to see are these models for describing the reaction kinetics agree with the experimental results or not. Then in each space, in each loop, we can add more hypotheses or experimental measurements data to make it more accurate and calibrate the reaction kinetics. This step is space independent, which as I said, the only purpose is to describe the reaction mechanism. And it means that we are not applying any geometry of reactor, or we are not considering the type of the reactor and so on. After that, we can add a space. We can add the geometry and dimensions of reactor. But there are key steps of simulation. First is that build geometry of the phenomena, and then add material properties, do the setup for different physics, adding different physics, carefully describing the phenomenon, and then generating mesh, solving the multiphysics model, and then evaluating the results and optimizing the results. But let's go to the example that we want to simulate a reaction on COMSOL. For that, we're using this propane steam reformer reaction, which at the first reaction, we use this rate law, and reaction order is 2. And for the second reaction, this is a reversible reaction, and for kinetic mechanism, we use mass action law. And these are assumptions. Assumption is that we are considering all these gases as ideal gas, and also we considering that these species are perfectly mixed, and the initial temperature is 800 Kelvin, and we know the initial concentration of each species. After opening COMSOL Multiphysics, you can see these two options. Blank model is that the model is blank itself, and you need to add dimension of geometry, different physics, and a study type by yourself. Model wizard, it's going step by step. First step here you can see is selecting the space dimension, because our simulation is space independent, so we click on 0 dimension. Then we need to add physics. Click on chemical species transport. We're going to use reaction engineering module. Then we add it to this below list of added physics interface. By clicking this one, you can also remove this added physics. But I want to continue our study with this physics, and then I'm clicking on time dependent and done. It's need a little time to generate the tree of design. Yes, here we can see here that under the component 1, this dot shows that this component 1 is 0 dimension, and the only physics here added is reaction engineering model. Then the short term for this physics is RE. I want to define these two reactions. I'm right-clicking on the name of reaction engineering, reaction, and then I'm going to add this formula: propane plus water, and this sign shows the irreversible reaction: hydrogen plus carbon monoxide. And you can see that this chemical equation is not balanced. If I click on balance, the COMSOL automatically calculates the stoichiometric coefficient of each species. And then I'm going to add the second reaction. The formula is carbon dioxide plus hydrogen, and this time this equation is reversible, so I'm going to use this sign: carbon monoxide plus water. Balance. Also I can click on apply. Next step is to define the thermodynamic properties of each of these species. I'm clicking on global definition, right click, thermodynamics, thermodynamic system. Here all the species are on gas phase, and click on next. Propane, water, double clicking each of these species, and then they automatically added to the selected species below. Carbon monoxide, carbon dioxide, and the last one is hydrogen. And yes, all of these species are here. Then click on next. I'm using ideal gas because this was our assumption, and click on finish. Next step, we need to link thermodynamic of these species to the reaction engineering. By I click on reaction engineering, here is mixture properties. Check the thermodynamic system that can use here is gas system 1. Yes, here we use gas system 1. And the phase is gas, ideal gas law, and then we need to match each species: propane, carbon monoxide, carbon dioxide, hydrogen, and the last one should be water. Yes. And also we want to calculate the mixture properties of each species from the thermodynamic. Next step is to define the reaction, and then I'm clicking on this reaction here. Yes, the type of reaction is irreversible, correct. The reaction rate, we're going to click on user defined. The correct reaction rate should be like this, and the rate constant is 0.01. The forward order of reaction is 2, and the rest is automatically calculated by COMSOL. Then I'm clicking on the second reaction. Here the reaction rate calculated by mass action law, right? And for rate constant, I'm clicking on equilibrium constant. If I click on Arrhenius expression like this one, I need to add the value for frequency factor, temperature exponent, and activation energy, which I don't know these parameters. Then I delete the check of this box, and I want to COMSOL automatically calculate the rest of the parameters and constants. And we need to add our assumptions and initial values. I click on reaction engineering here. You can see the equations that this module used for calculation. The reactor type is batched, constant volume, and the volume is predefined by COMSOL. The energy balance here, the external heating is 5000 watt, and initial values. The temperature, initial temperature is 800 Kelvin. The initial concentration of propane is 1. For water is 1. And for carbon dioxide is 0.5. I think that all of them are defined. Let's click on a study. On time-dependent study, first we don't know how much time the reaction needed to be complete. Then we can put some time, like I consider 50 seconds, which after that I click on compute to see the result. Yes, here we can see that, okay, 50 seconds, it's more than enough, maybe 20 or 30, it's okay. And also here the results are automatically generated. You can see like what I interpret here from the concentration graph. We have, of course, temperature graph and etc. Thank you for watching this video. I hope that you enjoy and used all you learned from this tutorial and apply it to your work.